Good morning, students. In the last class, we started with machine independent assembler features, which are the desirable features of the system software which is needed. Anyway, these features are also illustrated using the SIC machine and SICXC machine as examples. First of all, last class we just dealt with the literals. Literals are specifying the character or string constants without declaring them in the as an operand directly in the instruction. That is done by using equal to sign along with the value. The value may be a character constant, which may be either an ASCII or an hexadecimal, or it may be a string constant. So either of these things could be the defined as your literals. So those values can be directly used. Something like as we use immediate values with integer type, we are going to use literals for defining the character and hexadecimal values. So, and we have seen the examples here. So in the traditional methods, we used to declare the hexadecimal variable and then use it the variable name or a constant name. So, but here we're going to directly specify the value, something like dd is equal to x indicating an hexadecimal, f5 indicating the value directly. So this way we can use the character constants directly in the instructions, which we call it as literals. Similarly, we have used LDCH str1 comma x, which is a copying of the string constant, which is new to the accumulator, character by character. But now instead of that, we are using LDA instruction and specifying equal to character, that is C new. Directly, we are specifying the value of the literal to be loaded to the accumulator. The entire string will be copied into the accumulator. No need to use index addressing for this. And these literals need to be allocated memory space. That can be done by using LTORG, which is an assembler directive. LTORG creates a literal pool in the place where this assembler directive appears in your program. Suppose in address 1003, if at all you have found an assembler directive LTORG, the literal pool for all the directly used character constants and string constants as literals will be allocated memory. So that's what is the task of LTORG. So if at all the question arises, if LTORG is not specified, then where will be the literals will be allocated spaces? These literals will be allocated space just after all the declarative statements that you have made in your program. And usually these declarative statements are written at the end of the program. After that, before the end, this will going to be allocated memory, which will automatically be done. But otherwise, if you have to specify specifically, that can be specified by using LTORG. The current location counter value will be taken as the space for your literals. Okay. Yeah. Moving on next we have something called symbol defining statements. This symbol defining statements can be specified by using an assembler directive EQU. EQU is a assembler directive, which we call it as equate statement. So the syntax goes something like this. We have a symbol that is any user defined symbol, EQU, the value. So this way we can specify. Yeah. And this helps us in specifying the constants. This helps us in specifying expressions. That's what is the advantage what we have in EQUATE. And this can't be used for uh, declaring variables. We have RESW and RESB for variables. But EQU is to equate a user-defined symbol with a value. That value may be absolute, means something like I'll tell AEQU 20. So the 20 is just simply declaring it as a what you call integer constant. Instead of telling a word and value 20, we can also use EQ, which is absolute way of specifying. We can also specify them relatively. That means A, EQ, B plus C. B and C should be either a variable or a constant, which should have been defined earlier. So such sort of thing, earlier or later, that constraint we don't have. So that's what is the use of EQ statement. You can define a symbol and assign it with a value. So the type of the symbol will depend on the value that is being allocated. Either it is an integer or it may be a what do you call character, right? So for example, here 0 EQU 0. 0 is the name of the symbol, EQU, and its value now I am assigning is 0. It equates the value of the symbol to this. And important thing is any user defined symbol will going to get the address or entry into the symbol table. Hence, our equating statement symbols will also get the entry into the symbol table with the address whatever is been specified. Okay. One more example. CNT count EQU 15. This way we can specify. And these EQU statements or these symbol defining statements we're going to visit again in our multi-pass assemblers, where this plays a very vital role. We're going to see how this leads to the multi-pass assemblers. That's what is we're going to see a bit later. Next, one more statement we have is, one more assembler directive we have is ORG, which is called as origin statement. What this origin statement takes is ORG followed by a value specified by the user. This is used to initialize the location counter with specified value. Suppose ORG 2000, if at all I have given, the location counter value, whatever it may be, the next location counter value will be initialized to 2000. So that's what is the thing. And here one important thing is that ORG can be used without a value. So you just can specify the assembler directive ORG without specifying any specific value. Something like 2000, you don't specify. Then what happens? The location counter value is initialized to the previous value, whatever the previous is then. So ORG, for example, we are assembling a program and you are started with 1000, 1000, 1003, 1006, something like that, it has gone. And you have given ORG 2000. So the location counter value will start with 2000, 2000, 2003, 2006, it goes on. But at some place you have written ORG, then it is going to start with the previous value of the whatever the location counter was there. So that's what is the use of this ORG. For example, you can see here, okay, we have a program here for this symbol definition, particularly ORG. You can see that 1000, the program is, we are telling string is the name of the program, start, and 1000 means the first instruction supposed to be given the address 1000. So at 1000 we have an instruction LDX with immediately with 0. Next at 1003 we have LDS with immediately value 10. At 1006 we have LDCH. At 1009 we have HDCH. And at yeah, and this is supposed to be 100C. Fine. The next instruction is at 100C. One second, let me make the correction. Okay, this is supposed to be 100C and 100A. Okay, right. Yeah. See, the addresses are assigned consecutively from row 2 till row 7. 1000, 1003, 1006, 1009, 1006 was again. Fine. And here at row 8, we are telling new EQU 2000. We are using a equating statement and assigning the value 2000 to the new user defined symbol, which is going to get entry into the symbol table. After that, we are specifying ORG new. ORG initializes your location counter to the value whatever is specified. Here we have specified new. New is equated to the value 2000. Means to say now your location counter will be initialized to 2000. Means to say the next consecutive instructions should be allocated space from 2000. So that's what is being done in row 10 and 11. That's the reason I have highlighted that. You can see that the next location counter value, which is supposed to be the next value of 100F, right? But now it is not. It is given the space. It is given the location counter value 2000, and 2000 is str1 which is a string constant, which is having this system soft. That's what is the string contents. String 1 is a character constant string, means that there is a string constant, and the next value of str2 is starting from 2008, because your system soft will consume 10 bytes from there. So the next one will going to start at 2008. So the string 2 is allocated 10 bytes of memory starting from 2008 to 2020. So this goes on. So this is what is the use of this org statement. So what's the advantage? You can have a look at this program. All the instructions are given the address starting from 1000. If at all you want to allocate a separate addresses or separate memory location for all the declaration, yes, of course you can do it by using org. Or else your program is having more than one subroutines and you want to assign a separate addresses for each subroutine. Yes, you can do it by using org. Or you have a big program wherein the main program starts and somewhere the subroutine is being called, and subroutine should be given a separate addresses. And again, when you return back, you are supposed to write the main program continuation. Yeah, of course you can use org without whatever you call the value or without the address. Then org will continue from the main program wherever it is been started. So this allows you to partition the same program and arrange it in different address spaces. So this is one of the machine independent features. So remember, all the machine independent features are some explicit features which are not mandatorily, which are some desirable features which has been included. Maybe it's a literal, or maybe it's a symbol defining statement, or it may be a for your org. All this comes into the same category. So this allows you to divide the program into parts, and I cannot call exactly the parts. Allocate the addresses in your parts 1 or different part of program in different addresses. That's what is the possible thing. And if you look at it, this absolute address, this doesn't have any impact at all. You are going for a relative address, right? So that's how we are doing it. Yeah, we move next. That's about 3 things. So we just started with the literals. Literals are assigned by using equal to and a value, which can define as news. You use to allocate or use the character and hexadecimal constant or strings directly in the instruction without declaring the things. Next, we went for literal LTORG, which will going to create a literal pool by allocating spaces for all the literals that you have used in your program. And then we went to equating statement, which will going to define a new user defined symbol, assigning it with a value, right? And org statement will initialize the location counter to the specified value. If no value is specified, then it is going to continue with the previous location counter value. That's what is the 3 things what we learned: literal LTORG, EQU, and org. Right? Next, we have something called expressions. This is of a certain use we're going to see. And assembler allows use of expressions in their declarative statements. So till now, either we declared an integer constant, integer variable, or character constant or character variable in the declarative statement using resb, resw, or else byte or word. These assembler directives we use to make the declarations. But on the right hand side of the declaration, either you had constant values for integer constants or character constants, but in case of variables, you had the size of the variable. If suppose I have told array resw 10, means I am trying to declare an integer array of 10 bytes. That means what we are trying to declare is 30 bytes, because each integer contains 10 bytes. So according to the size of the variable, the size and the space for each variable, the total addresses will going to be allocated. But expressions allow you to specify the size based on already existing variables or already declared or later to be declared variables or constants. Such thing is called as expression. Rather than theory, we can see it in the example. That's going to be the better way. Yeah, the expressions are evaluated into a single value or an operand address, and that is going to be same. So that's how it is going to be done. Yeah, let's see this. Arithmetic expressions. So in your expression declaration, what and all you can have? You can have arithmetic expressions, addition, subtraction, multiplication, division. You can also have constant symbols, constant values, or constant already declared. You can have the symbols, one symbol getting the value of other symbol, something like A is equal to B, fine. Or you can also have a star or an RHS of the right hand side of your what do you call expressions. The expressions are specified by using EQU, which is again a symbol defining test statement, which we have just seen. And here the star need to be discussed a bit. The star wherever it appears, please note carefully, the star wherever it appears on the right hand side of your EQU, indicates the current location counter value. The star appearing on right hand side of your EQU indicates current location counter value. Fine. Let's see the example. So we have a declaration here. Read address, something like you can think it as read address is the name of the symbol user specified, whatever it may. Read address reserve word 1. It's a integer variable consuming one word space. That's what is been specified. This is a normal declarative statement, right? Length reserve word 1. Again, we are declaring an integer variable whose size is 1. That means 3 bytes. Next, what we are telling, buffer is a name user defined symbol. Reserve bytes 1000 means we are declaring 1000 bytes. We are declaring a string of 1000 bytes, which is of the type character, and his name is buffer. These are all our normal declarative statements. Next we are going to see. Now we are telling buffer and EQU star. See, after the address is allocated for read address, length, buffer, whatever is the next location counter value, that will going to be the address of your buffer end. Buffer end is a user defined symbol specified by using equating statement, and that buffer end will going to now get the address at the current location counter value, whatever is that, right? Next, we have a max length, that is again a equating statement, that is again a symbol defining statement, which is equal to buffer end, which is containing the current location counter value minus the address of the buffer, Suppose, let's see the calculation. We'll discuss. Suppose, for example, have a look at this. Return address is allocated memory at, let me think, 1000. Then length will be allocated memory at 1003 because one word consumes 3 bytes. After length, the next address will going to be 1006. So your buffer address will going to be 1006 and 1000 bytes from there, right? So it will going to become 2006. 2006 will be your address of your buffer. 2006 minus 1006. So the max len value will be equal to 1000. So that's how the things works. We shall have a discussion on this. The expressions are classified into 2 categories. What are they? The expressions can be either a relative expression, the expressions can be either an absolute expression. What I mean is, absolute expression after evaluation gives you a value. For example, here, your max len equal to buffer end minus buffer will going to give you one value. But buffer end equal to star will give you a relative address, that is your location counter value. So those are those which are giving the address is called as relative expressions. Those which are giving you a value is called as absolute expressions. I repeat, those expressions which gives you an address relative to your location counter value is a relative expression. Those expressions which give you a value, whatever the value it is, that value, such sort of expressions, we call it as absolute expression. These are the two categorizations. The value of expression is related to the static address of the program, then it is called as relative. That means to the location counter, then it is called relative. If the value of the expression is not related to the static address of the program, that means your location counter, then we call them as absolute. That's the difference. Absolute, a value, not related to your location counter. Relative expressions, they give you a address related to the starting address of the program. That's the difference. Let's see the example. There is a possibility that relative expression can produce an absolute value and the reverse. This is our what do you call example of return address and all the things. Now have a look at this table. Return address, yes, it's a type of relative expression. For example, if the value given is 0030, yeah, 0030 is a place where you have allocated the memory. Length is again a relative addressing. For example, 1 second. This is supposed to be 0030. Okay. I think you people might have understood why I did this. Because when return address is given address at 0030, the next address will going to be 0033 because return address is an integer variable. It consumes 3 bytes. Writing 0038 is of no use, means meaningless, right? That's why. So the length will going to get the address at 0033. Perfect. Because it's also a integer variable, it will also consume 3 bytes. From there, buffer is getting the address 0036 because length will also consume 3 bytes. Buffer consumes 0036 and the buffer size is 1000 bytes per byte. So we are defining buffer end equal to star. Star is again relevant to the current location counter address. After allocating 1000 bytes for your buffer, your location counter value would have been 1036 because your buffer is getting the address 1036 and buffer end is getting the address 1036 because the size of your buffer is 1000 bytes. Okay, that's also relative. Then who is absolute? Yeah, the last one, max len, is absolute, which is giving you a value. The value doesn't depend on your location counter value. So which is buffer end, which is 1036 minus buffer, which is 0036. Obviously, we're going to get the size as 1000, which is a value, which is not the address. So this max len alone is a absolute expression. The rest all 4 of them are relative expressions. So either an expression can be relative or either an expression can be absolute. This way we can use the expression to create the values, and usually the expressions are defined using symbol defining statement EQU. The assembler directive EQU is used to do this, right? Okay. Next, we go to the next concept of program blocks. The program blocks, I'll just want to give you an introduction that it is logically, I'm repeating, it is logically partitioning your program. It is logically partitioning your program in a single file. Logically partitioning your program in a single file. Why I'm making it specific is, but the next thing that we'll learn is something called as control sections, which is actually physically partitioning your program. Means you write the program in different source files and then you assemble them, each of them separately, and then link them together. Such sort of thing we call it as what? Control section. Logically partitioning your program within a same source file, we call it as program blocks. We shall see this program blocks. The same program is in a same file may contain many programs. Logical partition. Right. The source program may contain executable instructions, data areas, loops, etc. in different parts. Okay. These blocks are assembled into a single block. When you are assembling, you have written main program, half of it at the beginning, then you have written some other part of the program, then you have written again some other part of it, everything. So subroutine 1 you have written, then subroutine 2 you have written, then again you have written the rest part of the main program. This is logical partition. But when you give it to the assembler, your first assembler, what it does, it will going to arrange all parts of the main program together, then all part of the subroutine together, and all parts of the second subroutine together, and then it will go into assembler. That sort of thing. That will be done by your assembler. So assembler first rearranges. You can write however you want. You can write it in different blocks, but these blocks, the consecutive blocks, are continuously attached together, and then the assembling will happen. Right? For doing this, we have an assembler directive called by the name use. Use is the assembler directive, what we're going to do. And here, the use assembler directive is used with a name. Whatever the name you are specifying, user defines the name. Use, besides that, whatever the name you are specifying, that will going to define a new block. That will define a new block. And you have used use, okay. The block name is optional. That's what I want to tell you. The block name is optional. By default, when you start writing the program, you have only one block. If you want a second block, you're going to specify it by exclusively using use specified by the new block. Similarly, how much ever the blocks you want, you can keep on creating. But whenever you use, means whenever you write use without the name, then those instructions belongs to the default block. As I told, by default you will be having one block, and you can create any number of blocks by specifying block use specified by a new block name. But when I just use the use assembler directive without specifying any block name, indicating that these set of instructions should belong to the default block of the program. That's what is the understanding what we're going to get. Right? Each program block may contain instructions from different part of the source program, and the assembler rearranges the instruction by grouping all those instructions belonging to the same block in one place. Okay, have a look at the example. This example is showing we have 1, 2, and 1. Means there is one default block. 1 second. Timeout warning. Okay. 2 user specified blocks and 1 default. This example is having 2 user specified blocks and 1 default. Yeah, have a look at the program. Name of the program is copy, and I am telling start from the address 000. Who is started from 000? The default block will be started from 000. Okay. 000, we have LDX instruction, LDA instruction at 03, and 06 is having STL instruction like this way, and we may have some more instructions also. We are not bothered about it. We have some more instructions. Fine, leave it. And on the next line, we are having an assembler directive use C data. Now the C data is a new block that we are creating. As a new block is created, again, your location counter value is initialized to 0. Why is it done so? Because to indicate that it is a new block. So use C data is making your location counter value 0, 0, 0. And then there are 3 instructions. After that, we have told use means the statements or the instructions next to it should belong to the default block. Should belong to your default block. See, these 2 instructions, LDCH and STCH, is not belonging to C data, but it is belonging to the default block which we created at the beginning. After some instructions, we have an instruction means we have used the assembler directive use C block, which is indicating that these following instructions should belong to a new block. It should not belong to a default block. It should not belong to C data, but it should belong to a new block that is called C block. And we have some 2 instructions there. And again, we have used just use means the next instructions should belong to default block. Means your default block is written in 3 places. First LDX, LDA, STL. After that LDCH, STCH. After that, one more STA. So these set of instructions belong to default block. 3 instruction is belonging to your C data. There is length alpha return address. And two instructions are belong to your C block. This is how we are logically partitioning the program into blocks, right? During the pass 1, location counter is initialized to 000. After pass 1, the assembler rearranges the statements according to the blocks and entry is made into the symbol table. Just have a look. This is our program and this is how the rearrangement is done. Now see there, LDX, LDA, STL, LDCH, STCH and STA according to their addresses also is being created as a default block. And those instructions, those three instructions that is belonging to your C data is arranged from, so you can see the address after 000F, the next address is 0012 is given to the first instruction of your C data, that is 0012, then 0015, 0018. Though your location counter was initialized to zeros for each block, after pass 1, it is given a continuous addresses. And the instructions belonging to C block is also getting the next addresses 001B and 001E, that is the addresses just after your what you call C data block. So then this is just in one single program with a continuous addressing. Though you have created the program blocks, your pass 1 erased all the blocks and given a continuous addresses, and this will be given to your pass 2. And after this arrangement only, the address for your length, alpha, return address, all these things are going to be allocated, and then the symbol table entry will be made. So this is how we can create the program blocks. Means you might write the instructions the way you want. So you can create a pool of instruction which is related to one thing, but that can be rearranged by your pass 1 of the assembler. So this is what is the thing. So we can again, in the next class, we just put some light on this particular program block, and then we continue with the next concept. I think the time up. So thank you for joining.